We will start reviewing for Wednesday's exam. Okay. And so we'll basically go through most of what we've talked about over the semester in abbreviated format. We'll talk about hypothesis tests, and most of the tests that we've talked through, I won't go through every one in detail, but just summarize most of the tests that are most widely applied and of greatest interest. We'll talk a little bit about confidence intervals, and so you should expect to be knowledgeable of confidence. Sorry, my phone rang and I've lost my screen. Okay. So we'll expect to talk about confidence intervals and the comparison contrast between confidence intervals and hypothesis tests. And so you should be familiar with those concepts, though the focus will be more on the hypothesis test and confidence intervals. We will have at least some coverage of that. We'll also talk about analysis of variance. The emphasis here will be on one-way ANOVA, and then lastly, linear regression, okay? And so again, the midterm will be this Wednesday, and the next slide details the format. So initially I was gonna have it go out at 8:30 and turn back in at 5 p.m., but I decided we'll just make it a one-day take home. So it'll go out at 8:30 on Wednesday morning and be due with a hard deadline of 8:30 on Thursday morning. And so again, it's take home, so open books, notes, computer, internet, etc. The general structure, I'm going to have roughly 5 short answer conceptual type questions, where this could include things like when we talked about type 1 errors, type 2 errors, statistical power, some of that content, understanding what the results of statistical tests mean. So I could give you output from some tests or some model results, and then I could ask you to interpret what those results mean. And so this will build off some of the discussion we had about hypothesis tests and p-values and some of the common mistakes that arise and things of that nature. Asking you to think about what some of the underlying assumptions of these tests are, what some concerns may be as you look at some of the results. So maybe there are important variables that haven't been included, or there may be some reasons why the information presented doesn't provide a compelling answer to the research question. And so I apologize because I'm being somewhat ambiguous here, but the intent of those questions is just for you to demonstrate your understanding of probability and statistics and the methods that we've applied thus far in the course, okay? And then for the quantitative portion, you'll be provided with 2 data sets. The first of those will be used to apply a number of the simpler statistical tests that we have learned, so different tests of means, whether that's in a parametric framework, so 1 or 2 sample t-tests, paired t-tests, etc., the non-parametric alternative. So Mann-Whitney U, the sign test, Wilcoxon ranked sum test, etc. And that would also be fair game for including ANOVA as a part of that. So as we've done in some of the homework assignments and some of the in-class examples, comparing the results of our normal 2 sample test to the more robust ANOVA procedures. And then the large portion will also be a multiple linear regression data set. So I will provide a data set to you and ask you to utilize that to estimate a multiple linear regression model, run model diagnostics, check the assumptions, describe what your results mean, and so forth and so on, okay? So that's what we're looking at from a big picture perspective. Does anybody have questions on the general format information? Okay, if not, we will get started with some review of the content we've been covering over the last few months, okay? Okay, so when we talked about hypothesis testing in general, we had indicated this is basically, there's a general 6-step process that's followed. And so does anybody recall the first step in our hypothesis testing process?
Defining hypothesis?
Yeah, so the first thing we're going to do is define our null and alternative hypotheses, right? And so what are statistical hypotheses, Falarin? Can you explain that to us?
Okay, let me just explain the way I understand. The hypothesis is what you are trying to if you have some data, what you are trying to test for in the data.
Right. So it's what we're trying to evaluate or assess. If we think about it formally, hypotheses are basically statements about what? Anybody?
The mean?
It could be the mean, yes. So hypotheses are basically statements about parameters, right? And so that's probably a good point to emphasize here. So very early on in the first lecture, in fact, we talked about the terms parameters and statistics, right? And so parameters are basically numerical measures that quantify some aspect of what? As compared to statistics, which are also numerical parameters which quantify some aspect of something else. I'm trying not to be too cryptic in the way I set this up. But so when we think about parameters versus statistics, what are the differences between those terms?
The parameters define the population, whereas the statistics define the data, the sample.
Right. So exactly. Thank you, Nishal. So parameters are basically quantities that describe some aspect of our population, whether that's the population mean or the population variance, or whatever the case may be. Oftentimes, we don't actually observe the entire population, and so as a consequence, we draw a sample from it, and we would calculate statistics, which would be representative of those population parameters, right? So we would estimate the sample mean, and that would provide us with an estimate of what the population mean would be. Likewise, we could calculate the sample variance, and as long as we're dividing by n-1 and not n, that will give us an unbiased estimate of the population variance. And so when we talk about hypotheses, hypotheses are basically formal statements about those parameters, okay? And we've talked about one sample and or one-sided and two-sided hypothesis tests. So we'll return to that on the next slide, but sometimes we'll assess whether or not a parameter is different between two populations from which two different samples are drawn, or if the parameter from a given population is different from some arbitrary value of interest in the case of a one sample test. And when we set up those hypotheses, generally we'll refer to them as the null and alternative hypothesis. And the null hypothesis is basically, and it's typically set up as an equality. And so going into our experiment or our research study, we're assuming that either, say, the means of two populations are equal to one another, or the mean of one population is equal to some reference value, as the case may be. And our alternative hypothesis then would be either that those means are different from one another, or that one is expected to be greater than or less than the other. And so once we've established those hypotheses, we'll establish a significance level. You know, typically we've talked about 0.05 being a common value there. And so when we talk about significance level, does anybody recall what that term means? Can somebody give me a nice quick definition? So our significance level is our probability of doing something. Doing what?
Is it making a type 1 error?
Right. So our significance level is basically the probability that we would commit a type 1 error, which is the probability that we would reject the null hypothesis when in fact it's true. And another way of thinking about it is basically it's a value we're going to establish, and even if there is a difference and if our null hypothesis is not correct, we would need to be able to collect enough evidence based upon underlying probability theory that there's a significant difference between those parameters based on the data that we've collected. Okay, and so when we say significance, we're basically, if we assume the null hypothesis is true, we would want to basically collect data and calculate the test statistic, and we would assess how likely it is that that test statistic would be drawn if the null hypothesis was true. Okay, so based on our sample, we're using that to assess our null hypothesis. And the less likely it is that the data conform to our null hypothesis, that would provide evidence that we would then want to reject the null. And so as a part of that, we establish some threshold value as to how large in magnitude that test statistic needs to be, right? And we do so by establishing that significance level. And so the lower the significance level, the less likely we would obtain that extreme of a value if the null was in fact false. And so consequently, low significance level means that we would need to calculate a relatively high value of the test statistic in order to reject the null. Okay, so once we've established the significance level, we'd go out and we'd collect data, or in the case of the exam, that data would be provided to you. We would calculate a test statistic, and we've gone through quite a few over the early stages of this course. Based on the result of that test statistic, we would compare that to our critical value, which again is linked explicitly with that significance level. And then we would want to draw conclusions as to what that means. And typically, we're going to either reject the null hypothesis, which means that we found sufficient evidence to refute, for example, the statement that the means are equal between two samples. If we don't collect sufficient evidence in order to reject the null, what do we claim then? Are we accepting the null hypothesis? Anybody?
No, you're just failing to reject.
Right. So in that case, and be very careful with the wording there. We're not accepting it and claiming that there's no difference in the means then, for example. Just based on our sample, we're failing to reject. We don't have sufficient evidence to claim that there is a statistically significant difference as it relates to that parameters in our null hypothesis. Okay. And so we talked about three different types. So we have the two-sided test. So going in, we may not have a good sense as to whether there's a direction one way or the other. We're just concerned with whether or not our sample is compatible or consistent with that null hypothesis. And so in that circumstance, we would collect data, calculate our t-statistic, and we would evaluate whether that test statistic is significantly larger than this critical value on the upper tail of that distribution, or significantly smaller or more negative than the lower value on this distribution. Okay. In contrast, we may have circumstances where we would have a prior reason to either suspect an effect in one direction or another, or we may only be concerned with an effect in one direction or another. And so we talked about the example, excuse me. We talked about the example of the motorcycle helmet law. And so in that case, we assumed that after that helmet law was weakened, we'd see an increase in fatalities. And so in that case, we may be concerned just with the top tail of that distribution. And so we may be evaluating the second set of hypotheses and using this portion of that distribution as our rejection region. Or conversely, if there's a circumstance where we would expect that a value would go down, or we'd see a negative difference, or one sample its mean is smaller than the other, one population mean is smaller than the other, we may be interested in this tail, okay? And so as we think about that, these critical values are selected such that they're going to include an area that's equal to alpha, where alpha is, again, the significance level that we had talked about on the preceding slide. okay? And so in the case of a standard normal or z-test, we would know that at alpha of 0.05, these critical values would be at plus or minus what? Does anybody recall? So alpha 0.05, a two-sided test, our critical z would be plus or minus.
$1.645.
So it would be 1.645 in the one-sided cases, right? So positive 1.645, there's a 5% chance we'd have a value as large or larger than that. And there'd be a 5% chance that we're less than or equal to negative 1.645, okay? In the case of a two-sided test, though, we want the top 2.5% of the distribution over here and the bottom 2.5% of the distribution over there. And so those critical values would be plus or minus
1.96.
1.96, right? Okay. And so again, that's essentially how we'd evaluate that. We'd either be looking at both tails in the case of a two-sided or either tail in the case of the one-sided test, okay? Type 1 and type 2 errors. So we've talked a little bit about these previously. Can somebody remind me what a type 1 error is or represents? Maybe Travis, I think you had already started us down this path.
Was the likelihood of rejecting the null when it's true?
Right. So when we reject the null hypothesis, when it's actually true, that's going to be defined as a type 1 error, and we'll generally refer to that as alpha or our significance level. And so that's one of the two general types of mistakes we can make. The other is a type 2 error. Can anybody recall what a type 2 error represents?
Failing to reject null when it's false.
Right. So in this case, we're failing to reject the null when that null is actually false. And so in that case, we'll refer to that as a type 2 error. We'll denote that as beta. And so when we think about this, we can represent this as a table. So what we're hoping will happen as a consequence of our statistical test is we'll either reject the null when in fact it is false, or we'll fail to reject it when it's true. And so alternately there, the problematic areas that arise is rejecting the null when it's true or failing to reject when it's false. And so those are type 1 and type 2 errors respectively. We can think about these if we look at the distribution of our test statistics. And so, for example, let's assume in this case, we've collected data and we're just going to start nice and simple. We're doing a one sample test of means. And so we have some assumed value that we believe our sample of data would be representative of. And so we collect data. And so that data is going to be represented by this red distribution here. The blue data or the blue distribution would be representative of our null hypothesis. And so we're only going to, so if we collect repeated samples from this red population here, it can fall anywhere within these bounds here. Okay, so this is basically a distribution of sample means of repeated samples. Most of the time we're going to sample data and the mean will fall relatively close to the mean of that distribution, but sometimes we'll end up with somewhat extreme values. And if the null hypothesis is true, the same applies there. If the null were true, we'd expect that most of the draws of those random samples would occur near to the mean value, and it would be relatively unlikely we would fall on either extreme here. And so as we think about that in concept, for our given test statistic, our distribution for the alternate hypothesis is centered at wherever that mean is of our sample data, right? And so we would compare the center of this distribution to where the corresponding critical value is. And if this distribution or that sample of data that we've collected essentially is beyond the critical value of our null hypothesis, we would then end up rejecting the null, okay? Now, in actuality, we never really know if our null is true or not. We're trying to collect data and empirically assess that. And so it's hypothetical how likely it is that an error has occurred, for example, because we don't actually know that an error has occurred in practice. But if we assume that the null hypothesis is true, we set up this threshold value, then whatever portion of this distribution, so this, whether it's 5% or whatever the case may be, if this distribution is centered within that region, which ranges all the way to positive infinity in concept, although it's going to be very rare, we have values that are very far out in the tail here, we would reject the null. And so if the null is actually true, this is the area that we're concerned about, and this is where those errors would occur. Okay, so it's whenever this distribution of our test statistic based on our sample data falls within this region, or in the case of a two-sided test, it would fall within either of those regions. That would correspond to a type 1 error occurring. Okay, is that clear to everybody? And then similarly, when we look at the probability of a type 2 error occurring, that would be represented by beta in this figure here. So in this case, we're conditioning it rather than assuming that the null is true. We're assuming that the null is in fact false, and that our alternate hypothesis is representative of that actual parameter, that population mean. Okay, and so it's different than that reference value we're comparing it to. And so in that context, we're interested in the entirety of this distribution that would fall within the rejection region, okay? Because this distribution needs to be far enough away from the center of that null hypothesis such that we can reject, okay? But depending upon how large the difference is or how much variability there is in our data, there may be a sizable portion of that distribution where we simply don't have enough evidence to reject because we're not able to exceed that critical value, okay? And so in this instance, obviously, we would be more likely to correctly reject the null if the difference between our mean based on the sample data and that reference value is large. That would shift the distribution out to our right in this case. Or if the variance of this distribution is relatively small, which would result in this being narrower, and so there would be less area to the left, in this case, of that critical value, okay? But this is basically the area of the distribution, or the probability that we would basically fail to reject the null when that null is actually false and should be rejected, okay? And then the complement to that we'll refer to as the power of our statistical test. And so that's basically the white area underneath the red distribution here. And so if in fact the null is false and this distribution is different, the red distribution is different or larger in this case than the blue distribution, we would be able to reject if we obtained a sample mean that was anywhere within this portion of that distribution for that alternate hypothesis, okay? Does that make sense? Any questions on the big picture stuff here? Okay, at any point as we go.
Yes, I have a question.
Yes, go ahead.
So in a statistical test, we fixed alpha, let's say for a 0.05, but we don't talk about beta, like what's beta in a statistical test?
Okay, so good question. We haven't formally calculated power, for example, as a part of this class. And so when we're calculating power, we're basically in that case, instead of assuming that our null is true, we're assuming that our alternative distribution is true, okay? And so we could actually calculate that statistical power because, for example, let's say that we calculated our test statistic, and so these values, rather than being distributions of our mean, let's assume these are distributions of our test statistic, okay? So T would be equal to 0 at this point where that null hypothesis is centered. And let's assume, to make the numbers easy, this distribution is centered at 2. So we've calculated a test statistic of 2. We're beyond that critical value, so we'd reject the null hypothesis in this case. And so what we could do then is we could, since these data are essentially already normalized, So we know this distribution is centered at 2. We know we're going to reject that distribution in this specific case, but we would also reject until we got to a value as low as negative, as low as 1.645 in this case. So we're basically 0.35 standard deviations beyond that point, okay? And so we know if this is a standard normal distribution, for example, we could calculate explicitly what this area is right here, okay? So we can just basically kind of shift and rescale, and that would just be equal to the cumulative standard normal distribution up to a value of negative 0.35. Okay, that would give us what this area is here, so that would give us our probability of committing a type 2 error. The power of that test would be the probability of being greater than or equal to that value of negative 0.35 from the standard normal. Okay. Hopefully I was thinking as I was talking through that, so hopefully everything came out clearly. Does that make sense?
Yeah, thank you.
Okay. And again, we haven't done that explicitly up to this point. I kind of wish we had, although I did just walk you through it. So you won't expect to see that. You actually have to calculate the power, but just that is something that is useful to know. Now, in practice, we typically, you're not oftentimes going to see power reported in statistical tests, with the exception if we fail to reject the null hypothesis. Occasionally, you may see that reported. So, for example, if these were overlapped quite a bit with one another and there was just a very small portion of the red distribution that fell in this area, that would be a second piece of information, but it's somewhat redundant with our actual test statistic and with alpha to a degree. So they're related indirectly to one another, but we can explicitly calculate those probabilities. And again, when we calculate that, we're operating under the assumption that this alternative hypothesis is true, okay? All right, any other questions on the big picture stuff? Okay. So the first test that we talked about was the one sample z-test. And so in this circumstance, we were basically collecting information from a sample of data, and we were assessing whether or not the mean of that sample was different from some arbitrary reference value or population mean that we're comparing against, okay? And so in that case, we use a z-statistic, and the formula is as shown here. And can somebody remind me what the symbols stand for in this equation? So the z-test is equal to x bar minus mu over sigma divided by the square root of n. What are those respective quantities, Folarin? So what's x bar in this case, Folarin? Oh, sorry, you're muted. Oh, there we go.
X bar is the X bar is the sample mean.
Yep, x bar is the sample mean. Mu is
population mean.
Yeah, that's the population mean we're comparing against. What's sigma?
Sigma is the standard deviation.
The standard deviation of the sample or the population?
Sigma is standard deviation of the population.
Correct. And what's n?
N is the sample size.
Yes, correct. Thank you very much. And so in this case, our null hypothesis is that our sample mean is equal to whatever our population mean or whatever that reference value of interest is to us, okay? And so we would reject when our sample is incompatible with that assumption. And so that would mean it would be incompatible if this calculated z-statistic was either very large or very small. And so that's going to occur if one of three different things, generally speaking, is true. The first of those, if there actually is a large difference between that sample mean and the population parameter that we're comparing it to. Okay, so as that gets larger, our test statistic is going to get larger, and we're going to converge towards the rejection regions of that test statistic. Okay. The other two circumstances would be if our standard deviation is relatively small, because as that gets smaller, the shape of our distribution, if we think back, the middle of that normal distribution becomes more peaked and the tails become flatter. And so there's a lot more points that are clustered near to the mean then in that case when we're sampling data. And so as our variance or standard deviation gets smaller, that test statistic gets larger. Or alternately, as our sample size increases, that same phenomenon will occur. So this bottom quantity is basically an estimate of what the standard deviation of this difference is, okay? So this is our standard error, to use that terminology we had introduced previously. And so generally speaking, the parameters that we're interested in appear in the numerator here, and in the standard error is the denominator, and that's just the standard deviation of whatever that upper quantity is, generally speaking. Okay. And so we take these calculated values, we'd compare them to the critical values from the standard normal table. And so earlier we had made reference to the 1.645 number, and so that's right in here. That's where we get to the 95th percentile. And then likewise, the 1.96 number corresponds to the top 2.5% of that distribution. We know this table is symmetric, so if we were operating on the other side and looking at negative values, the 2.5 percentile would be negative 1.96, and the 5th percentile would be negative 1.645. Okay. And unfortunately, we typically don't actually know what sigma is in practice, and so we would estimate sigma using S. And so an alternative to the one sample z-test is the one sample t-test, where all of these variables are as presented previously, except now we're using that sample standard deviation. And you should remember, I haven't included a review of the very simple summary statistics, but you recall the population variance is basically the average squared deviation of all of our points from the mean of the sample. And so that would just be calculated sigma, or sigma squared in this case, would be the summation of each observation minus the sample mean, that quantity squared across the sample divided by n. So again, it's the average sum, the average squared deviation of each point from the mean. In the case of a sample, the formula is nearly identical, except we subtract off, we divide by n minus 1 rather than n, because as we demonstrated, we'll tend to systematically underestimate the value of the variance for a sample. And the reason for that is that the sample is typically going to have a mean that's slightly different than the population. And so consequently, we'll tend to systematically underestimate, okay? And so in practice, this is relatively straightforward. X bar, S, and N are all based on our sample data, and we're comparing those against some reference value. Our critical table in this case is going to depend upon what level of significance we select and what our corresponding degrees of freedom are. And so to refresh everybody's memory, our degrees of freedom are basically the number of observations that are free to vary when we calculate these test statistics. And so when we calculate our t-test, we need to assign a value of X bar in order to calculate S. And so what that means in practice is that we need at least 2 observations in order to calculate a standard deviation. And so we lose one of those 2 parameters essentially because we need to calculate the sample mean prior to calculating the sample standard deviation. And so we would have n minus 1 degrees of freedom associated with this test statistic, okay? And as our degrees of freedom increase, or as our sample size increases, we tend to have more confidence in our results, right? Which makes sense intuitively. And so as a consequence of that, if we look at our t distribution here, as our degrees of freedom increase, what that does is it decreases the level or the value of our critical value that we need to compare our test statistic against. As that sample size and the associated degrees of freedom approach infinity, this is just converging to our standard normal distribution, okay? And so application here is completely analogous to what we do in the one sample z-test, okay? Now we can take the same general concepts that we just covered, and we can also apply them when we're comparing differences between two populations using two sample means. And so in that case, as you'll recall, our null hypothesis is generally going to be simply that mu1 and mu2 are equal to one another. So this difference will basically drop out of the equation, and we'll just have the mean of the first sample minus the mean of the second sample, dividing by the standard error, which in this case is the ratio of their variances divided by their sample size. And so we'll take then the square root of that quantity. Everything else is evaluated in a manner analogous to the one sample case. So we'd compare this value to the corresponding critical value using our standard normal table. And we would then make a determination as to whether those sample means are different from one another or not, okay? Now, as in the case of the one sample test, we typically don't know sigma 1 squared and sigma 2 squared because we're not able to measure the entire population. And so we would use a t-test as an alternative here. And so the two cases here, there's students T and Welch's T. You'll notice the setup here is almost identical, except instead of having sigma 1 squared over n1 plus sigma 2 squared over n2, we now have sp squared. Does anybody recall what sp squared represents?
Pooled variance.
Correct. So that's our pooled variance. And that's basically going to be a weighted average of the variances between these two samples, okay? Now, under students' test, we're making an assumption about the variances of those two samples. And what is that assumption that we're making? Anybody? We use students when what's true of our variances?
We assume the variances are equal.
Correct. So students is appropriate when those variances are equal to one another, and hence in that case, we're pooling those variances and calculating their average as a consequence instead, okay? Now the degrees of freedom for this test as compared to the one sample test when there was n-1 degrees of freedom, in this case, we're calculating a sample mean for each of those samples in order to calculate their respective variances. And so we would have n1 minus 1 degrees of freedom for the first sample and 2 minus 1 degrees of freedom for the second sample. And so in total, we'd have n1 plus n2 minus 2 degrees of freedom, okay? And so we would use that degree of freedom to pull the corresponding critical value from our critical t-table, okay? And the calculation of the variance are just basically weighted by the sample size. So we're giving more weight to whichever of those variances is being drawn from a larger sample, okay? In cases where the sample sizes are equal to one another, this is just the straight line arithmetic average of those respective variances, okay? If the variances are not equal to one another, we would use Welch's t-test instead. And so the setup here is nearly identical. The only difference is that instead of using a pooled variance here, we're including each of the individual sample variances in this respective calculation. And so since those variances are not equal to one another, our primary concern here is that if one of the variances is particularly small, that could inflate the value of this t-statistic larger than it should be, and we may end up rejecting the null when in fact we shouldn't. And so consequently, we calculate the degrees of freedom using this formula right here, where those degrees of freedom are basically weighted by how large that difference is in the variances between those two samples, okay? So as the differences in the variances get very large, those degrees of freedom will shrink down from what we would see in students' case, where that is just n1 plus n2 minus 2. In the extreme case, in the opposite direction, when those variances are in fact equal to one another, then this will just reduce to that quantity n1 plus n2 minus 2. Okay. Otherwise, application there is pretty straightforward and similar to what we've talked about previously with students test. Okay. The paired t-test we would use in special circumstances. When would we use the paired t?
When the two samples are dependent.
Yeah, so the paired t-test is going to be used when the two samples are dependent on one another. Now, what do we mean by those samples being dependent?
For example, we are collecting data from same objects or individuals over time.
Right, exactly. So if we're conducting observations on the same unit, whether that unit is a person or a place or a thing, I guess, if we're observing the same unit repeatedly over time under different conditions, perhaps, we would expect that there would be some natural correlation then, or there'd be dependence obviously between those samples, because you would expect that individual observations made on those same units would tend to be consistently higher or consistently lower than you would see just when comparing random observations between those two samples, okay? And so in that context, instead of us simply comparing the difference in means and variances between those samples, we would be interested in comparing the means and the variances of the differences between those observational units, which within those samples, okay? So if we've got 10 observations under two different conditions, we would just take the differences of those 10 observations. And so that mean difference would basically be represented by X bar sub D here. So that would be the average of those differences. We're generally comparing that against whether there's any difference whatsoever. So we would set this mu equal to 0. SD would be the standard deviation of those differences. And then N here would be the sample size, which would be the number of observations in each of those respective groups, okay? So we may have 20 measurements on 10 units. It would be the 10 units that would be our corresponding sample size here, okay? And in this case, our corresponding degrees of freedom would be N minus 1. And so we talked about this a little bit in some of the preceding lectures. So there are a few things that should be considered when you're determining whether or not to conduct a paired t-test. So first of all, there should actually be some hypothetical reason why it would make sense. So you know, for example, that there's natural pairing between those observations. And then it's a question of how strongly correlated those measurements are, because if we were to conduct a two-sample test, we'd have roughly twice the number of degrees of freedom as we would have in the case of the dependent test. Okay, so students or Welch's, you could get up to N1 plus N2 minus 2 degrees of freedom, where in this case we just have N minus 1 degrees of freedom. And so as a consequence, that correlation would have to be relatively strong for us to sacrifice those degrees of freedom. And so this test statistic then would need to be relatively large compared to its corresponding critical value, okay? All right, we also talked a little bit about confidence intervals for those means and differences in means. And so I think I'll just show here these for each of the tests we've talked about previously. These are the corresponding confidence interval calculations. Now, can somebody refresh my memory? What exactly is a confidence interval and how does it relate to a hypothesis test? Does anybody recall? So we can use confidence intervals in an analogous manner to assess our hypotheses of interest. But what we're doing here mechanically is we're basically taking data related to our sample, right? And so as we look at our quantities here, we're generally conducting these again with the t rather than the z-test, but I'm including all of those here for completeness. But we collect data on our sample. So we have a sample mean in the case of a one sample test, or we have a difference in sample means in the case of students or Welch's test, or we have a mean difference in the case of the paired t-test. And then we're constructing bounds on that using data from our sample. So basically our standard error terms. So the standard deviation divided by the corresponding sample sizes. And then we're also using information about our t-distribution, okay? And so what these bounds are basically giving us then are based upon our sample data. These are constructing lower and upper limits such that under repeated samples, we would, this range would include the true population parameter 95% of the time or 99% of the time, or whatever we're assuming for our confidence level, where confidence again is just 1 minus alpha. Okay, so 1 minus our significance level. And so if we construct a 95% confidence interval, that would give us a range. And so 95 times out of 100, that range would include the actual true population parameter. Okay, and so in this case, we would then test against whatever our hypothetical or presumed value of that parameter may be. And so we'd see whether or not the mu that we're comparing against in the test statistic is included within that range of values, okay? If it's included within that range of values, what does that mean? So for example, if we construct a 95% confidence interval around X bar, and that interval includes mu, or we construct a 95% confidence interval around the difference in the means of those samples, and that range includes the actual mu1 minus mu2 value, or in that case, it includes 0 if we're just testing whether or not there's a difference. What does that mean if that range includes mu or 0?
It means that we cannot reject the null hypothesis.
Exactly, right? And so we're approaching the hypothesis test using similar strategies here, but just the setup is slightly different here. So in this case, we're using the sample data to construct these bounds and then assessing whether or not the parameter is actually included within those bounds. Whereas in the case of the hypothesis test, we're just comparing that sample statistic to that hypothesized parameter value explicitly, okay? And in that case, we're testing whether or not that test statistic is outside of those bounds. And if it's not outside of those bounds, then we would fail to reject. Whereas in this case, similarly, we're constructing a range based on sample data, and those limits, we're assessing whether or not our parameter actually falls within there, or in the case of just testing whether there's a difference, whether 0 falls within those limits, okay? The same thing comes up when we talk about regression models, and we check whether or not the 95% confidence interval includes 0 for those individual regression parameters, as an example, okay? Any questions on the confidence interval stuff? Okay, the next few slides.
I have a question on slide 12.
Okay, let me back up real quick then. Okay, slide 12.
Yeah, so here you have sigma 1 as sample variance. Is that not supposed to be like S1?
So we use the z-test when our variances are known to us, which generally is not going to be the case. They're not going to be known to us. And so we would use S in the case of our t-test. So in student's case, or the most direct analogy to the preceding formula would be Welch's, where we got S1 squared instead of sigma 1 squared, okay? So it's sigma if we're using a z-test because the variances are known to us. It's S if we're using the t-test because in that case our variances are unknown and we're estimating them using sample data. Does that make sense?
Yep.
Okay. All right. I think we were on 17. Okay. So The other thing we talked about were some non-parametric alternatives. And so we may end up in circumstances where some of the underlying assumptions don't hold. And so primarily we're assuming that our data are normally distributed. And so if that's not the case, and we may have cases where our distribution is skewed, so we have a disproportionate number of extreme observations, whether that's on the positive or negative side. And so in that case, we can use the Mann-Whitney U-test as an alternative to Student's or Welch's t-test. And so in this test, all we're doing is we're taking all of our individual observations across both of the samples, and we're ranking them from 1 to n, okay? And so we're summing the ranks within each of those respective samples. And so that sum of the ranks for the first sample is R1, the sum of the ranks for the second sample is R2. And then we're calculating this U statistic and using that to assess whether or not those distributions are significantly different from one another, okay? And so the mean and variance of that U, so if we conducted repeated samples, the mean would simply be N1 times N2 over 2, where these are the sample sizes of those two samples. The standard deviation is given by this calculation right here. And so we would just evaluate this as a z-test and assess the hypotheses accordingly, okay? And so what we'll tend to find here, this test isn't going to be as powerful, generally speaking, as our t-tests if in fact our underlying assumptions are true, but it will provide us with better and more robust results if that normality assumption is violated. Okay, so generally speaking, you'll get the same conclusion from either of these tests, but this test will be preferred if that normality assumption is not met. Okay. We were presented with two other alternatives that would have been appropriate for one sample test of means or as alternative to the paired tests. And so the simplest of those was just the sign test. And so in this case, if we're comparing our sample mean to a population parameter of interest, we would just count the number of times in our sample we had a value that was either larger or smaller than that difference. Or in the case of an analogy to a paired t-test, we would look at each of those differences between the observation and we just code whether or not those differences were positive or negative as we compared sample 1 to sample 2 or vice versa, okay? And so that can also be used in the case of a z-test here. And so our expected number of pluses or minuses, again, if the null is true, is just half of whatever that sample size is. The corresponding standard deviation is just the square root of our sample size times 0.25. And so we'd compare this test statistic to our standard normal table as we would normally, okay? And then the one limitation of the sign test is that it's very general. So if that difference is, 0.1 greater or 1 greater or 10 or 1,000 or 1,000,000 greater, it's just one plus sign there. And so a more robust alternative to the sign test is the signed rank test. And so this is conducted similarly, except in this case, we're calculating the positive and negative differences, and then we're ranking those differences essentially, okay? And so we rank the positive and negative differences between those pairs, and those ranks, or the sum of those ranks, would then be evaluated against, again, the z statistic here, okay? So our average rank between those positives and negatives is given by this formula. The standard deviation of those ranks is as shown here. And then we evaluate it against the standard normal as we do in each of the two preceding tests, okay? So again, very, very similar results in nature. This will tend to give us better results than we'd see in the sign test because it's accounting for the sign of those differences as well as the magnitude. And again, each of these would be appropriate for comparison against a one sample t-test or a paired t-test, okay? All right, we also talked about two different tests of variance in the one sample case where our null would be that we're comparing the variance based on our sample data to some hypothetical variance of interest to us. The chi-squared test is just equal to our degrees of freedom, which is n-1 in this case, times our sample variance divided by whatever that reference variance is that we're comparing against. And so in this case, we would go to our critical chi-squared table and we would compare to the associated critical value. And so the upper tail here is as indicated here. So if your test statistic was larger than this, we would be beyond the top 5% or 2.5%, whatever the case may be of that distribution. And then on the bottom side, if this variance were smaller than that reference value, we would reject at the corresponding lower end of that distribution, okay? And so that's when we're comparing the variance of one sample against the reference value. We also frequently will compare the variances between two samples. And so again, this is probably about the easiest test that we'll run. So the F test is just the ratio of those respective variances. And so you just take one variance divided by the other. It's completely arbitrary which one is in the numerator or the denominator here. You'll just want to make sure you choose the correct critical value. And so as we look at the F tables, these are slightly different than the prior tests that we've introduced because there are both numerator and denominator degrees of freedom in this case. So we'd have n-1 degrees of freedom, or sorry, n1 minus 1 degrees of freedom for the numerator, n2 minus 1 degrees of freedom for the denominator. And so we'd select the critical value accordingly here, okay? Now you'll notice this is for 0.05, so this is only the top 5% of that distribution. If we wanted the bottom 5%, we would just take the inverse. So for example, if we had, let's say, 20 numerator and 20 denominator degrees of freedom, that critical value would be 2.12. And so that would correspond to the upper critical. The lower critical would just be 1 divided by 2.12. So that'd be a very small number over on this side of the distribution. Okay. All right. I think that gets us through all of our 1 and 2 sample tests that are of interest. We talked about a few others, including tests of proportions and perhaps a few others that I'm not thinking of at the top of my head. But everything we've covered up to this point is what the primary focus will be on. The other thing that we've talked about over the past few weeks, there's been 2 primary topics. The first of those was analysis of variance, and the second of those was linear regression. And so in the case of ANOVA, what we're doing is we're taking the total variability that we're observing in our dependent variable, so in our Y variable, and we're breaking that into 2 component parts, right? So the portion of that variability that's due to our treatment, which would be basically differences between our samples, and the error portion, and so that would basically just be comprised of random inherent noise, error, variability in our data, okay? And so in long form, what we're doing here, if we have 2 or more groups, we can take the means of those respective groups, and so those means, as you recall, are denoted as yi dot bar. And so that's just telling us that we're taking the average within group I, and the dot means it's over all observations. Subtracting that from that, our overall mean, and squaring that quantity. And so this is giving us a sense of how much distance there are between each of those individual group means or sample means and the overall mean of our data. And then this sum of squares for the error term is just giving us a sense of how much variability there are between those individual data points and their respective group means, okay? And so if we take those 2 differences in sum, those will add up to the total sum of squares here, which is just taking the difference of each of those individual observations from the overall mean of the data set, okay? And so as you can see here, we would tend to support we'd have more evidence in support of a difference in means as this quantity gets very large relative to this quantity, okay? And so we'll present these results in an ANOVA table. So our sum of squares for the treatment, error, and total. Degrees of freedom for the treatment sum of squares is A minus 1, where A is our number of groups or samples that we're comparing. Capital N here is just going to be A minus N, so the number of groups times the number of observations within each group, minus A, and we're always going to have N minus 1 degrees of freedom for our total sum of squares. Okay, so total sum of squares divided by its degrees of freedom would just give us our variance back. And so we're partitioning that variance into two components, the mean square for the treatment, which is just our SS treatment over A minus 1, and the mean square of our error, which is just SSE over N minus A. And then the ratio of those two estimates gives us an F statistic, which we compare against the same critical table we saw on the preceding slide, okay? And in the case of this F test, we'd only be concerned with the top tail of that distribution, okay? And we've just worked through this on the homework, so hopefully this is relatively clear with anyone. Did anybody have any questions on ANOVA? I guess I think I've got one more animation here, and that would relate to, now if we reject the null in this case, that would basically mean that at least one of those means is different from the others. We don't necessarily know which. And so there are several different tests we can conduct after the fact, with one of those being Fisher's least significant difference. And so in this case, we would just take 2 times our mean squared error. And so again, that mean squared error is basically, that's an estimate of sigma squared. So that's an estimate of our variance in this case. And so 2 times that variance divided by n, taking the square root. So this would be the standard error of those differences times the corresponding t-statistic. Excuse me. And so we would calculate this least significant difference, and we would then compare the differences between each of those individual pairs of means against this critical value here. And in cases where it was greater than this least significant difference, we would claim that those means are significantly different from one another. If the differences are less than this LSD value, then we cannot reject the null for that specific pair of means, okay? All right, and then what we've talked about most recently has been linear regression. And so in the simple linear regression case, we have a model where we're relating y to one independent variable of interest x. And as a part of that, we're trying to estimate beta naught hat and beta 1 hat. And to do that, to determine the estimate of our intercept term, we can rearrange this equation. And so prior to getting to that step, we would generally estimate the slope parameter first. And so that is equal to SXY, which we see in the top here, divided by SXX. And so all we're doing here, we're summing our XYs, we're subtracting the sum of X times the sum of Y over N. The denominator here is identical, except that we're swapping in X for Y here. And so we've got the summation of XI squared across all observations. The sum of X across all of our observations, that quantity squared divided by N. And it should look familiar to you here. So this is basically just the total sum of squares for X. So analogous to what we had seen on the preceding slide for ANOVA. And then this is basically showing us the covariance between X and Y, essentially, how those change together versus the corresponding unit change we would see in X. And so the t-statistic to evaluate those hypotheses of interest are as shown here. We talked about R squared, which represents the proportion of the total variation in our Y variable that's explained by X. We can calculate that in either of the two manners illustrated there. And then we can also present these results in terms of an ANOVA table where we have our regression, error, and total sum of squares. Our degrees of freedom here, P is our number of parameters in the model, and so that would include our constant term. And so in the simple linear regression case, we would have 2 minus 1 or 1 degree of freedom. Excuse me, again, we would have N minus P, error degrees of freedom, and then N minus 1 total degrees of freedom. Again, calculating our mean squared regression over our mean squared for the error here. And so that's how we would do it for simple linear regression. As we expand to multiple linear regression, the setup would be the same here. The underlying algebra gets a bit more complicated here, but we would still be working with the same general formulas. So the t-statistic would just be each of our individual parameter estimates divided by its corresponding standard error, which in the multiple linear regression case would require us to go to the variance covariance matrix to look at the diagonal elements for each of those. But again, we're not asking you to work through and calculate that. So for the purposes of the midterm, it's fine to work through this in SPSS or R or Excel or whatever you may so choose. Okay. I believe that is the last. Oh, sorry, there's one more. So the other thing we talked about towards the end of last week were the underlying regression assumptions. The first of those is that y is linearly related to x. How do we assess that assumption? So how do we determine if y is linearly related to x?
We can simply plot y versus x, or we can plot the residuals.
Yeah, so the easy thing would be to just plot y versus x. We could also look at the residuals. So if we plotted the residuals versus y hat or versus x, that if that assumption were violated, we would see some sort of trend in the data points. So maybe we would see increasing and then decreasing, or decreasing and then increasing. So maybe there's a second order function there. Or maybe it's increasing, it looks exponential, so we might want to look at a log transform. And we talked about a few of the different transforms there. But again, you can either plot the data directly, y versus x, or plot the residuals versus our predicted or versus our x values. The other assumptions are also all directly related to those residuals. So first of all, they need to be uncorrelated with one another. And secondly, they need to have constant variance. And so again, in this case, we're plotting those residuals. And so I guess let's do a real quick timeout. What's the residual?
The difference between estimated y and the actual y.
Yeah, so our residual is basically quantifying the error that's inherent in each of our observations. And so we denote our residual generally as E sub I. So that's the error associated with observation I. And that's just going to be equal to yi minus yi hat. So each observation minus its corresponding predicted value. Okay. And so we're plotting those residuals against y hat. We're plotting those against x as well. And we hope that they're not correlated, so we don't see any patterns, whether it's increasing or decreasing or cyclical, whatever the case may be. And we would also hope to see constant variance. So those points are scattered equally in terms of their magnitude from 0 when we plot versus predicted or versus x, okay? If either of those assumptions are violated, we'd want to look at some type of transformation for our data. The fourth assumption is that those errors are normally distributed, which we could assess using either a normal probability plot or some of the other tests that we have covered but not talked about today, like the Kolmogorov-Smirnov test or the chi-square goodness of fit test. And then the last assumption is that those x's are going to be independent of one another. And so there are various ways we could assess that, and that would include, we talked about the variance inflation factors, so regressing the x's against one another just to assess whether or not there's correlation there, okay? And so as we work through regression for Wednesday's exam, you know, with that data set, you'll want to run through, and for each of the variables that's included in your final model, assess the degree to which these assumptions hold ultimately. And apologies if you hear my dog in the background, but fortunately we're almost to the end here. Let me close the door real quick. And I believe that is now my last slide. So at this point, we've got at least a few minutes. If anybody has any last minute questions, and like I said, the plan for Wednesday morning, I will post the exam on D2L such that it opens right at 8:30. So I'll just code that in. And then I'll close submission at 8:30 a.m. the next day. So please do not submit late. Make sure you get it in at least a few minutes early there. But I decided to give you the full day just because who knows what you have going on with your other classes and things. And I always have daycare pickup at the end of the day. So last minute questions would be very problematic. And so hopefully that works out well for everybody. I think I'm still in the process of going through the homework, but it looks like everybody has a really good handle on stuff. I think we had a lot of good questions over the weekend, but I'm rambling. Do we have any questions from any of you?
Question about not about the exam, but about the next deliverable for the paper. So you said you want us to have preliminary analysis by the end of the week, right? So what should that contain?
So for the term paper stuff, I'll restructure those deadlines a little bit. The primary thing I want at this point is hopefully everybody has their data set in hand. If that's not the case, and so I guess just show of hands or thumbs as the case may be, how many of you have your data set in hand at this point? Okay, I'm waiting for 17 seconds and hopefully I see virtually all of them go up. And how many of you don't have your data yet at this point? Not to call anybody out specifically, but yeah. So yeah, we'll definitely want to get moving on that because as we move forward, we're going to start using some of the class time for check-ins on the project, and we'll have some working sessions as well. And we're going to start to introduce, starting next week after the midterm, some additional families of models that can be used in regression frameworks. And so virtually everybody should have all the tools they would need for their final project within the next few weeks, basically. So by the end of the month, I think we should be in good shape. And even if your data is not particularly well suited for linear regression, it's generally a fairly good starting point. So let's plan to do we'll do a check-in on that, I guess, on Monday for Lauren, just to see where everybody's at. But in the meantime, if anybody has questions about the data that they're maybe in the process of collecting, just let me know. And then we can circle back. But sorry, we're talking kind of across purposes. Any other questions either in the term paper or the exam? Okay, going once, twice, 3 times. Okay, so I will try to get this posted right away before my 10 o'clock meeting. If you have any other questions between now and Wednesday morning, just let me know. I'm happy to record a short video or send out a response email if there's something that's unclear or that you have some questions on. So, okay. All right, thanks everybody. Have a good one. Oh, wait, there's one message in the chat box. Oh, that was just a thank you. All right, have a good one.